Hello, and welcome to this video series on algorithms. This is part 11 of Module 4 on greedy algorithms. In this section, we will study the Huffman coding algorithm. First, we introduce the concept of a coding problem. Coding is a process of representing text from one alphabet using symbols from another alphabet. In modern computer systems, characters are typically represented using ASCII. Under ASCII, each character is encoded as an 8-bit binary number. For example, the letter A is encoded as 01000001. Thus, ASCII allows computers to represent human-readable text using binary numbers. There are two major types of coding schemes. The first is fixed-length coding, where each character in the target alphabet is represented using a code of the same length. ASCII is an example of fixed-length coding, since each character is encoded using 8 binary digits. Another example is the genetic code, where each amino acid is encoded by a fixed-length sequence of 3 nucleotide letters, also known as a codon. Another type of coding scheme is variable-length coding, where different characters may be represented using codes of different lengths. Consider a simple alphabet A, B, C. Under a fixed-length coding scheme, we might encode A as 00, B as 01, and C as 10. In this case, the string ABC is encoded as 000110. On the other hand, under a variable length coding scheme, we could encode A as 0, B as 1, and C as 10. Then, ABC is encoded as 0110. This encoding is shorter than the fixed-length version. As a result, variable-length coding can reduce storage requirements as well as transmission cost and delay. This efficiency is the main advantage of variable-length coding over fixed-length coding. However, variable-length coding introduces a potential challenge during decoding. If the codes are not carefully designed, decoding may become ambiguous. Consider again the variable-length coding scheme, where A is encoded as 0, B as 1, and C as 10. When the code 0110 is received, it can be decoded either as ABC or as ABBA. This ambiguity highlights the need for additional constraints when designing variable length codes. To avoid decoding ambiguity, we require the coding scheme to be prefix-free. A prefix code is a coding scheme in which no code word is a prefix of any other code word. For example, consider the scheme where A is encoded as 0, B as 1, and C as 10. This is not a prefix code, because the code for B, 1, is a prefix of the code for C, 10. In contrast, consider the scheme where A is encoded as 01, B as 11, and C as 001. This scheme is prefix-free, since no code word appears as the prefix of another. Given a prefix code, decoding can be performed unambiguously using a simple greedy strategy. We scan the encoded bit string from left to right until we find a prefix that matches a valid code word. Because the code is prefix-free, this prefix cannot be the start of any other code word. So the decoding is unique. We then remove the decoded prefix and repeat the process on the remaining bit string until all bits are consumed. For example, suppose A is encoded as 01, B as 11, and C as 001. Given the encoded string 0100 11101, the first valid prefix is 01, which decodes to A. Removing this prefix leaves 00111001. The next valid prefix is 001, which decodes to C. Continuing this way, the entire string is decoded as ACBA. When using variable length coding, we must design a prefix-free code to ensure unambiguous decoding. However, the prefix constraint restricts our design choices and may increase the total code length. Therefore, beyond being prefix-free, a good coding scheme should also minimize the expected code length to reduce transmission cost and delay. To quantify this, we introduce the average bit length, or ABL. For a coding scheme gamma, the ABL is defined as the sum over all characters x of fx times the length of gamma x, where fx is the expected frequency of x, and gamma x is its code word. The value ABL of gamma represents the expected number of bits required to encode a single character. For example, consider the alphabet A, B, and C with frequencies 0.5, 0.3, and 0.2 respectively. In the first coding scheme, A is encoded as 11, B as 01, and C as 001. The resulting ABL is 2.2. In the second coding scheme, A is encoded as 11, B as 001, and C as 10. The resulting ABL is 2.3. Both schemes are prefix-free. Since a smaller ABL implies a shorter expected encoded length, the first coding scheme is preferred. We can now formulate the following computational problem. Given an alphabet and the frequency of each character, design a prefix-free coding scheme that minimizes the average bit length. This problem is known as the optimal prefix coding problem. We now examine key properties of optimal prefix codes, which naturally lead to the corresponding algorithm. Since modern communication systems use binary representations, we focus on binary prefix codes, where code words consist only of zeros and ones. A binary prefix code can be naturally represented using a binary tree. In this representation, each internal node has two outgoing edges. The left edge is labeled 0, and the right edge is labeled 1. The leaf nodes are labeled with characters from the target alphabet. The code word for a character is given by the sequence of edge labels along the path from the root to its leaf. Because any two root-to-leaf paths must diverge as a match, no code word can be a prefix of another. Thus, the set of code words defined by the tree is prefix-free. For example, in the binary tree shown on the right, the character A is reached by following two right edges. giving the code 11. Similarly, B is encoded as 01 and C is encoded as 001. We now formally prove proposition 1, which states that the codes obtained from root-to-leaf paths in the binary tree form a prefix code. We prove this claim by contradiction. Assume that the resulting coding scheme is not prefix-free. Then there exist two characters, x and y, such that the code word gamma x is the prefix of gamma y. This implies that the root-to-leaf path corresponding to gamma x exactly matches the initial portion of the path for gamma y and terminates earlier. Therefore, the endpoint of the path for gamma x must be an internal node of the tree. This contradicts the assumption that all code words correspond to leaf nodes. Hence, the codes derived from root-to-leaf paths in a binary tree must be prefix-free. Given proposition 1, we can solve the optimal prefix coding problem by constructing an appropriate binary tree. Our goal is to design a prefix-free code that minimizes the ABL. In the tree representation, the length of a code word equals the depth of its corresponding leaf. Therefore, reducing the depth of leaf nodes, especially for high-frequency characters, helps reduce the ABL. Without loss of optimality, we can restrict our attention to full binary trees, in which every internal node has exactly two children. We now formalize this intuition. Proposition 2 states that any binary tree that represents an optimal prefix code must be full. That is, every internal node has exactly two children. We prove this by contradiction. Suppose there exists an optimal binary tree that is not full. Then it contains an internal node with only one child. Let U be such an internal node, and let V be its only child. We claim that we can modify the tree by removing the edge UV, which strictly reduces the ABL while preserving the prefix-free property. To justify the claim, we analyze how removing the edge UV affects the resulting code. Consider the figure on the right. Let a purple path denote any root-to-leaf path that passes through the edge UV, and let a green path denote any root-to-leaf path that does not. After we bypass UV, we need to show that the code remains prefix-free. In particular, we verify three cases. First, any two code words from purple paths remain prefix-free. Second, any two code words from green paths remain prefix-free. And third, any code word from a purple path and any code word from a green path remain prefix-free. We first prove that any two purple paths remain prefix-free. Recall that both purple paths contain UV. Before removing UV, the corresponding code words were prefix-free. Therefore, the two root-to-leaf paths must diverge somewhere after node V, meaning that they have different suffixes starting at V. Removing UV only deletes the common prefix segment up to V. It does not change the part of the path after V. Hence, the two paths are still different, and neither can become a prefix of the other. Therefore, the two purple paths still correspond to prefix coding. Second, we show that any two green paths remain prefix coding. Recall that both green paths do not contain UV. Therefore, removing UV does not affect either path. Since this path corresponded to prefix coding before the removal, they continue to do so afterward. Finally, we show that any combination of one purple path and one green path remain prefix coding. Recall that the purple path contains UV, while the green path does not. Since node U has only one child V, any path that reaches U must continue through UV. Therefore, the two paths must differ before reaching node U. Removing UV does not affect this earlier divergence, so neither path can become a prefix of the other. Hence, the two paths still correspond to prefix coding. As a result, we can remove the edge UV from the original binary tree and obtain a prefix coding tree with a strictly smaller ABL. This contradicts the assumption that the original tree is optimal. Therefore, any binary tree that represents an optimal prefix coding scheme must be full. Next, we discuss another important property of an optimal prefix coding tree. Since our goal is to minimize ABL, Proposition 3 states that characters with lower frequencies should be assigned to deeper leaves. We prove this proposition by contradiction. Assume there exists an optimal tree that assigns character X to a leaf node U and character Y to leaf node V, such that Fx is greater than Fy, but depth of U is less than depth of V. In this case, we can swap the code words of X and Y. This preserves the prefix-free property of the coding scheme, since only leaf labels are exchanged. After the swap, the ABL is strictly reduced. This contradicts with the assumption that the original tree is optimal. Therefore, in an optimal prefix coding tree, lower frequency characters must be placed at deeper leaf nodes. At this point, we have established two key properties of an optimal prefix coding tree from propositions 2 and 3. First, an optimal tree must be full. Second, characters with higher frequencies must be placed at shallower depths, while lower frequency characters appear deeper in the tree. Because the tree is full, every internal node has exactly two children. Therefore, when the tree contains more than one node, every leaf must have a sibling. It follows that the sibling of a deepest leaf is also a leaf. Hence, a full binary tree must contain at least two deepest leaf nodes with the same depth. By proposition 3, these two deepest leaves should be assigned to the two characters with the lowest frequencies. This greedy observation directly leads to the Huffman coding algorithm, introduced by David Huffman in 1952. We now describe the Huffman coding algorithm. We begin with a wrapper function that initializes the recursive process. The input is S, a set of character frequency pairs from the target alphabet. In line 1, we construct a forest T, where each character forms a single node binary tree. We denote the tree corresponding to a character X as Tx. Since each character appears exactly once, the sizes of S and T are equal, and both match the size of the target alphabet. In line 2, we recursively combine trees in T to construct the optimal binary prefix coding tree. We now describe the recursive tree construction process. Line 1 handles the base case, where there's only one symbol to encode. In this case, the forest T contains a single tree, which we return as the optimal prefix coding tree. In line 2, we identify the two characters with the lowest frequencies, denote them as y and z. In line 3, we remove y and z from S and introduce a new character omega, whose frequency equals the sum of the frequencies of y and z. Let the resulting set be S prime. Note that S prime contains one fewer element than S. In line 4, we create a new tree, T omega, and attach the two trees, Ty and Tz, as its children. In line 5, we remove Ty and Tz from the forest T and add T omega, forming a new forest, T prime. The size of T prime is 1 less than that of T. Finally, we recursively apply this process to the updated symbol set S prime and forest T prime. Here, we illustrate the forests T and T prime from two consecutive recursive steps. In the earlier recursion, the forest T contains two separate trees, Ty and Tz. In the next recursion, these two trees are merged into a new tree, T omega, whose root has Ty and Tz as its left and right subtrees. As the recursion proceeds, the number of trees in the forest decreases, while the height of each tree increases. Because characters with lower frequencies are merged earlier in the process, they ultimately appear at deeper leaf nodes in the final binary tree. The recursion terminates when only a single tree remains in the forest. This tree is the binary tree that represents the optimal prefix coding scheme. We now prove that the Huffman coding algorithm minimizes the ABL. Proposition 4 characterizes how the ABL changes when two trees are merged during the recursion. Let T prime be an existing binary tree, and let T be the tree obtained by expanding T prime to include the two lowest frequency symbols, Y and Z. Then, AB out of T prime equals AB out of T plus Fy plus Fz. The tree T prime is shown on the left. Let the depth of node omega be D. And recall that F omega equals Fy plus Fz. In T prime, the contribution of the root to omega path to the ABL is D times F omega, or D times the sum of Fy and Fz. Now, consider the tree T prime, shown on the right. In T prime, the symbols Y and Z are placed as children of omega. So the depths of both root to Y and root to Z path are D plus 1. The combined contribution to the ABL is therefore D plus 1 times the sum of Fy and Fz. Compared with T, this increases the ABL by exactly Fy plus Fz, which proves the proposition. We now prove proposition 5, which states that the Huffman coding algorithm minimizes the ABL. We prove this proposition by contradiction and by induction. Let T be the binary tree produced by the Huffman coding algorithm, and assume that T is not optimal. Then there exists an optimal tree Z such that ABL of Z is less than ABL of T. By proposition 2, the two lowest frequency symbols must appear at the deepest leaf nodes in any optimal tree. Let these symbols be Y and Z. Removing the two corresponding leaf nodes from Z yields a smaller tree, Z prime. By proposition 4, we have AB out of Z prime equals AB out of Z minus Fy minus Fz. Now consider the tree T. Since the Huffman coding algorithm also places the two lowest frequency symbols at the deepest leaf nodes, We can similarly remove these two leaf nodes to obtain a smaller tree, T prime. Again, by proposition 4, a bit out of T prime equals a bit out of T minus Fy minus Fz. Because a bit out of Z is less than a bit out of T, it follows that a bit out of Z prime is less than a bit out of T prime. We can repeat this removal process on both Z prime and T prime, each time eliminating the two lowest frequency leaf nodes. After each step, we obtain smaller trees Z double prime and T double prime such that a bit out of Z double prime is less than a bit out of T double prime. We continue this process until both trees are reduced to single node trees. At this point, we obtain a bit out of Z single is less than a bit out of T single. However, this is impossible since any single node tree must have the same ABL. This contradiction shows that our initial assumption that T is not optimal is false. Therefore, the Huffman coding algorithm minimizes the average bit length. At last, we discuss the implementation and time complexity of the Huffman coding algorithm. Since we repeatedly need the lowest frequency symbols, we store the current symbol frequencies in a mean heap. Let the number of unique symbols be n. We can build the mean heap in O(n) time. In each recursion, we extract the two minimum frequency symbols, y and z. Each extract mean operation takes O log n. So extracting two symbols costs O log n time overall. We then insert the merge symbol omega back into the heap, which also takes O log n time. All remaining operations in the recursion, such as creating an internal node for omega and attaching the two subtrees, take constant time. Therefore, each recursion costs O log n time. Each recursion reduces the number of trees in the forest by 1. Starting from n single node trees, we need n-1 merges to end with one tree. Hence, there are n-1 recursion in total, and the overall time complexity is O(n) log n. Thank you for watching, and see you next time.